Welcome everybody to Archive Dives with Oxen.ai. This is a weekly series where we dive into interesting research papers in machine learning and AI and try to tease out some key insights that you can apply to your own work. If you're new here, welcome. Feel free to introduce yourself in the chat. We do this live every Friday with the Oxen.ai community and post them on YouTube for anyone who can't attend synchronously. Some quick background on us. Oxen is building a tool chain to help you collaborate and iterate on machine learning data sets like the ones used in these papers. We're putting together a Git/GitHub-like collaboration experience optimized for storing million row CSVs or millions of images, video, audio, or text. If you have any type of that data, feel free to upload it to Oxen and join our Discord if you have any questions there. Today, we're going over the Medusa paper, which is a super interesting technique from the teams at Together.ai that's tackling the problem of next token prediction in LLMs. Usually when a LLM predicts the next token, they're limited by a single softmax having to make and stick to that decision for the next word. And this paper has a cool tree-based attention mechanism to try to predict multiple subsequent tokens in parallel and give the model multiple candidate continuations while verifying them at the same time. Our presenter today is Daniel Varoli from Zapata.ai, and this is his second time presenting an archive dive. Super impressed with his depth of knowledge on the first one and excited for what he's going to share with us today. So that being said, I'll kick it over to you, Daniel.
Thanks, Greg. Thanks for let's hope that this paper lives up to the hype, the expectation that you've set, or my presentation of it rather. Okay, so I'm gonna share the screen. When you talk about LLMs, right, and you talk about generating tokens, you usually think of generating one token, and there are some problems with that. And in general, kind of the big problem is that the LLMs are kind of slow, right? So when you're doing inference, they can be slow, and the bigger they get, the slower they get. And so kind of what the authors of the paper talk about is that the bottleneck isn't necessarily that your GPU can't do the math fast enough, but that there's a lot of data transfer. So the kind of the GPU is sort of sitting waiting for data to be transferred. And and if you think about the forward pass of an LLM, at least my understanding of it, because I'm not really a hardware or GPU expert, but kind of the understanding that I got is that as you're doing a forward pass, you have to move a lot of stuff, like weights and the inputs, and you have to move it from this high bandwidth memory, which I understand can be at least a type of RAM on the GPU, and you have to move that from that to the kind of the GPU cache for further computation. And the cache is going to be not going to necessarily be is not that big, and so you're basically doing a lot of movement back, a lot of data transfer, and the kind of the actual computation is waiting for those transfers to happen. And so that's where the bottleneck comes in. And if you think about doing all of that work and getting a single token out, that's, well, not really efficient. GPUs tend to excel in settings where you can parallelize things. So, this kind of having to wait to do this one step at a time is, well, underutilizing the GPU's computational potential. So basically what we want to do, and what the paper talks about, is that we want to make the operations more arithmetically intensive, so actually get more flops for the same amount of data movement. And we want to make, do less of those operations. And if we can do that, we can speed up the whole process. So there are a few techniques, and one is, I think, kind of going to be familiar, is batch inference. So the idea is that, right, you, instead of doing inference one sample at a time, you're going to do that. You're going to kind of batch them together. But yeah, so the idea is that you have this this batch inference. You put multiple batches together, and you do a forward pass. And so kind of my hand wavy explanation of why that's better is, well, because you still have this huge model, right, and all the weights, but you're processing multiple inputs, and so I guess you kind of still do the same amount, or roughly, or you might not be doing the exact same amount of data movement, but you're moving those weights and reusing them for a bunch of the inputs. So you're not doing the same amount of movement for every input. You're kind of being more efficient and doing less movement, but getting more flops out, and sort of that's how you profit in terms of how fast, kind of your arithmetic intensity. So that's good. The only problem is that with LLMs, there is this thing called KV cache and a bunch of other things which are using a lot of memory, especially with big LLMs. And that puts a limit on the size of batches you can use. And so that's kind of one limitation. So then a natural thought is to say, okay, well, what if we just reduce the size of the KV cache? So that's one way, and that gives you a higher batch size. The other thing you can try and do is say, okay, well, there's this technique called quantization, which is that instead of having all the weights and all the parameters and everything in 32-bit or 16-bit floating point numbers, you could do there are techniques where you can store the weights, activations, and everything in a mix of 8-bit or even 4-bit or even 1-bit apparently now, and maybe some 16-bit operations, which essentially just means that you're using less. Your model is basically smaller. So you have a smaller approximation of the full model, and hopefully you keep the performance. But so that's one other thing you can do. This is the paper that mentions this 1-bit LLMs. I haven't read it. It's just something that came up on my LinkedIn feed. So I don't know what it really talks about, but I guess maybe, I don't know, 1-bit LLMs. I'm also always weird because I've seen a few like not prank papers, but like people will post papers with ridiculous results and they're not actually real papers. So I'm just letting you know, I haven't read this, so I don't know what this paper talks about, but maybe. In any case, 4-bit or 8-bit, the whole idea of quantization, I think, still makes sense. And so then there's another technique, which is speculative decoding. And it's, I guess, a fancy way of saying guessing. So, autoregressive generation, right, usually means you generate tokens one by one. But does it? Does that have to be the case? And I put together a little meme. There we go. So, maybe you don't actually need to generate them one by one. What if you could do many tokens in parallel? And that kind of sounds like a crazy idea. At least it certainly did to me, just because I've always been used to just generating one token at a time. So like, how can you generate more tokens at the same time? You need the previous tokens to predict the next token, right? And the idea here is that, well, yes, but what if you could guess, right? What if you could, or speculate, what the future tokens could be? So essentially, you're saying, all right, I'm gonna guess that the next 5 tokens are some tokens, and then I'm gonna verify if those are actually correct using the original model. And if you just happen to get those 5 guesses correctly, you just generated 5 tokens in one forward pass. So, and this is why I said the speculative decoding is just, I think, a fancy way of saying guessing, is that you're guessing, but as you'll see, the whole point is, can you guess well, right? Can you not just do random guesses over like a vocabulary of 60,000 tokens? Can you be smarter about your guesses? And so essentially, right, if we can speculate or guess well, we might be able to get more than one token per inference step. And ideally, we can get a bunch of them. Well, maybe not too many, but a bunch. And so I'm going to go over the normal way of how you do things usually, right? And that's, you would generate these tokens one at a time. So my professionally drawn, illustrations is you have a single token, let's say token 0, you feed it to your big LLM, you get some probability distribution out, you sample, you get token 1. Now you feed 0 and 1. And I'm not, there's more things maybe going on like cache, KV cache or whatever, but let's just pretend a simple case here. 0 and 1, you still get 2 output probability distributions. You sample from the kind of the final one, you get your second token, or token 2, or token 3, whatever, position 2. And then you do the same thing again, and now you generate token 3. So overall, you just did 3 forward passes, right? And you got out 3 tokens. So, okay, that's what you'd usually do. But here is where, let's take a look at an example of good guessing or good speculating. So I really shouldn't. Well, okay. So you're given 0, right? You're given token 0, just how you had here. And then you say, all right, I'm going to guess token 1 for the next one, and I'm going to guess token 2 for the next one. So now what you feed to the LLM is actually the 0 plus the 1 guess plus the 2 guess at the same time. You get 3 probability distributions, and then you sample them. And let's say, wow, your big model actually agrees that, yeah, it also thinks that the token that follows 0 should be 1. So you accept that as a good guess. then you have the same thing for your second one, also good guess. And you also get to keep the final one because, well, you got two good guesses, which the model agrees with. So naturally, the third one is also going to be a good token. So in a total of two guesses plus one forward pass, you actually got three tokens. So, and I think an important part here is to realize that you can generate three tokens in a single forward pass if you're feeding three tokens. So it's kind of like, normally you can't do this because you don't know what those tokens are, right? You need to generate them first. But if you guess them, you can hope that you guessed well. And so kind of just to show the other side of this is let's take a look at bad speculating, right? So if you're not very good at guessing, as you do the same thing, but given 0, you guess 3 instead of 1, and you guess 2. So now you feed your 0, 3, 2 sequence to the LLM, get 3 probability distributions, and you see that, oh, okay, well, I messed up. So the big model thinks that the next token after 0 should actually be 1, but I guessed 3. So it's a bad guess. I'm going to ignore all my guesses afterwards because clearly I messed up. But I still get to keep my 1 because, well, that's what the model predicted. And so the idea here is that now with 2 guesses in a forward pass, you still get a token. Now this is probably a bit worse because you have extra overhead in guessing, and depending how you guess, that's going to dictate, what that overhead looks like. But if you can have a good guessing strategy that sort of avoids these cases where you're just dead wrong immediately, you can speed up and you can go faster. So that's kind of the basic idea behind the speculating or speculative decoding. And there are different kinds of it. So it just feels like different flavors of guessing essentially. So you could do random guessing, which is probably not very good. So then there's the speculative decoding with the smaller or faster draft model, and then verified by the big model. So that's kind of like the previous approach that the authors are kind of trying to improve upon in this paper. And then there's the Medusa paper, which is sort of like the guessers built into the model itself. I want to note that this Medusa idea isn't exactly what the paper's contribution is, because the idea of what they set up actually comes from a paper in 2018. But I think my understanding is they improve it and they add a way this kind of tree attention is like the big part of what their contribution is, in addition to the other things.
Quick question for you.
Yeah.
Zach had a question in the chat around how long it takes to actually do that step where you're verifying the guess and assessing the quality of the guess with the larger model compared to just generating that token with the model one after another in the first place.
Yeah, that's a good question. So in terms of forward passes, this is a single forward pass as opposed to, let's say, 3 forward passes, right? But of course, there's going to be some additional overhead. I don't know exactly what that looks like, and it probably depends on what you're doing and how you're actually verifying. So we'll talk about that a bit later. But so I would say it's like the cost of it is 1 forward pass plus some additional overhead. And that is where, if your strategy is really good and you're generating a bunch of good guesses, then that overhead is going to be less than. So let's say your overhead, you managed to replace 5 forward passes with a single verification step, right? Chances are the overhead is going to be lower than if you had to do 5 forward passes. But yeah, so the idea is, I think in terms of how long it takes, is 1 forward pass plus some additional overhead of verifying, because you do need to, there is a strategy of how you do the verification. It's not just like, I think the strategy isn't too complicated, or I guess it depends on the strategy, but yeah, so that's the rough answer, is that it's 1 forward pass plus something else, and depending how good you are, that something else might be worth it just because you're saving a lot overall.
Perfect. So that's why it really hinges on the quality of the guesses so much and the quality of the guessing strategy. Great.
Yeah, exactly. So yeah, if you have a terrible guessing strategy, you might be worse off actually. So yeah. And I'm going to quickly talk about the speculative decoding with this draft model, just because I think for me, was very helpful to understand how that works. And this is from a blog on Hugging Face. So the idea is you have this smaller model, they call the draft model, which let's say is like something like llama 7 billion, right? And you use it, it's supposed to be faster. So you use it to quickly generate 5 tokens, for example. And then your main model, which is something like llama 70 billion, right? So 10 times bigger, is then used to verify those sequences the predictions. And so the idea is that up to the point where they stop aligning, you get to keep those, plus like the last one at the end, whichever the model predicts. And Yeah, so essentially, instead of doing, in here, right, guessing is done by this assistant or draft model. And the thought is that, hey, well, you know what? This assistant model is probably pretty good. Like if it's a 7 billion parameter transformer LLM, it's probably going to be good enough that it can, you know, sort of save us some tokens. So that's the idea with the speculative decoding with the draft model. And but yeah, that's what is sort of how the verification happens is you have your guesses and then you feed them to the main model, and then you know that verifies it. You're not doing anything special. The verification is just literally a question of, does the model agree with your predictions? But instead of generating those predictions in several forward passes, you do it in one go because you already have your kind of speculative sequence ready to go. So the Medusa idea is basically saying, well, okay, what if we just don't have the draft model, right? There's a lot of problems associated with this. Like you need to manage two models, which is potentially awkward in certain inference settings. You have to choose a draft model, so it might not be obvious what to choose. I mean, I guess if you have like llama 7 billion, llama 70 billion, this kind of seem like natural choices, but you know, it might be a case that just doesn't work for you. So you need to experiment with different draft models. And then if you wanted to do some kind of fine tuning, that also becomes a pain because you're still having to potentially fine tune this not that small LLM, right? So 7 billion is small, but it's still not trivial in you know, if you have certain resource constraints. And what Medusa proposes, or rather this kind of idea that Medusa builds upon, rather I should say, is having multiple decoding heads. And originally this didn't make sense, but then I actually understood that basically it's like saying, okay, we're going to have more than one language model head at the end, and each additional head is responsible for generating like extra tokens into the future. And to give you an example, I pulled up the description, or sorry, like the printout of what the like Falcon 7 billion looks like in Hugging Face, right? And so at the end you have this LM head. So that's your normal case. So with Medusa, my kind of rendition of what this would look like is you'd have a bunch of these Medusa heads following, and each one is sort of responsible for, so, you know, given an input sequence of length t, the LM head, language model head, is responsible for predicting token t+1. So that's kind of what your usual case is. And then each Medusa head is responsible for predicting some t+i token into the future. And so as you can guess, that means you need to train something here, but you know, we'll talk about that a bit later. So I think it's worth going through an example of how that actually works, because I think it's good to know that there are extra heads, but what does that actually mean and what that actually looks like? So if you generate tokens with your Medusa heads, right, you have your big LLM, you feed a token 0, you get your embedding, or like the last logits, like the, you know, right before your final, I guess, yeah, sorry, the hidden states, not necessarily the logits. Well, before the language model head. You would feed that, you get some probably a distribution with somewhere with the softmax, right? And then you sample to get a token. So with Medusa heads, you just add additional matrices that are kind of like this. It's not actually single matrices, but that's the rough idea, is that you add like additional blocks that then do predict, you know, token 2, predict token 3, so kind of a few positions into the future. And the idea itself is coming from here, paper from 2018. As you can see, they're doing pretty much the same thing. The idea that I think Medusa extends, or their contribution essentially, in addition to other things, or one of the things that their contribution is this ability to actually look at multiple candidates simultaneously with this tree attention. And if you notice here, we're only predicting one speculative sequence, right? So 1, 2, 3, that's it. And if we reject something, that's it. We're kind of done. We have to, you know, right? So we don't have any other options to consider. It would be kind of cool if we could have like a bunch of them, right? Not just one, and we could evaluate them at the same time. So that's really what we'll get into. A quick note on the parallelization, because I think that's worth stating, is that, so why is this actually, what is this, why is this faster? Or why would this be helpful? Well, the idea is that if you have these heads, right, they're different matrices, but they're getting fed the same inputs. So in theory, you could just split them up, right, and just do this operation in parallel. If you kind of think of it how, like, you know, you have a sequence of 10, you're feeding it through the same language model head, sorry, of 10, like, embedding matrix or vectors, you feed them through the same language model head. Here you're kind of doing the reverse. You have the same inputs, but they're going through a bunch of different new language model heads. I'm going to pause here if any questions, just because there's a lot of stuff going on.
Is there an aspect here of how how state space models handles tokens and long sequence length happening in each of these heads, or does it relate to that at all?
That's a good question. I'm not sure. I think this is I don't this idea originally comes from 2018, so I don't know if it precedes state space models because I don't know when those came around originally. I know that like Mamba and so on have been big recently, but I don't know if the idea when the idea originated. So to answer your question, I'm not sure.
I have a good answer for that. So state space models, you could in theory add a layer at the top of them that tried to predict multiple possible tokens. But the state space model itself is more like the big LLM at the bottom here and only has kind of like one hidden state space that is trying to update. It's more like a recurrent net.
Mm.
So you could use this in combination with the state space model is what I'm saying.
Yeah, I feel like that would make it like a super bionic. That this in combination with the state space model would be like mind blowing.
Yeah, that could be cool. Is this what was the base LLM that they used for this, Daniel?
They tried a few different ones, so like Vicuña and then Llama, or sorry, well, they tried a bunch of different like yeah, but Vicuña, Llama, I think, and then Zephyr,
Cool.
in the range of 7 to 33 billion.
They are like your traditional transformers that they're putting on top.
Yeah. They also have some. They have a repo, and they have some saved. I think they have a saved Vicuña model, or they have one where they have this Medusa heads built in on Hugging Face. So, but yeah, they use regular transformers. It's built on top of the
That'd be a fun combination. Medusa plus Mamba. It would make sense too.
We could make a new model and call it. What was that? Who was the guy in on the Discord who said flying spaghetti monster as the new name? Was that Kaiser? The name for his new model would be, because all of the good names are getting taken. Yeah, this
Yeah,
plus
Mambusa from Paul. Nice.
Yeah.
Love it.
Okay,
Cool.
thank you.
Yeah, thanks, Rick, for answering that. I wasn't sure the answer, but that's I think that's a cool. It'd be interesting. I'm be surprised someone's already working on this, but it still would be a cool idea to try. And so okay, so we got to the part of generating candidates, but now it's like okay, so you also need to verify them, right? Because well, you want to make sure that what you're speculating is in alignment with what your big LLM would say normally. And so now a note is that this is this process is what it is as far as I can tell based on the paper itself, the code, which was really hard to read, but I still managed to get something from there. And then there's some comments on Reddit that were really helpful in trying to understand what's going on here. But the idea is as follows, right? You have your sequence. Let's say you generated sequence. So you have your 0 as the input. And I think I might be missing an image, but okay, well, you essentially you say you have your 0 token, you predict token 1, and then you also your heads predict 2 and 3. So these are in brackets. So 1 is actual model prediction, 2 and 3 are Medusa head speculation from 2 parallel heads. So you then feed this sequence 0, 1, 2, 3 back to your model, and let's say it predicts something like 1, 2, 3, 4. So the LLM confirmed 2 and 3 as the Medusa guesses, right? And it also gives us 4 because again, we got the right choices before, so we can take the next token as well. So in total of 2 forward passes, 1 to generate like the candidates, and then the second one to verify, you get 4 tokens. So pretty good, and you can imagine that if you extend this to more Medusa heads, you could do better potentially. So that's a rough idea. And now there's a strategy on how you actually accept things. So, but a quick note on what happens if we mess up, right? And this, just want to mention, this is kind of similar to what we discussed earlier. There's not necessarily anything different in terms of like the idea remains the same. But what if we mess up, right? Again, so if we have 0, 1, 2, 3, we feed that to the model, and then the model actually outputs 1, 2, 6, 7. Well, we say, all right, well, 2 was a good guess, but 3 clearly was wrong. So our run of good guesses ends at 1. We only get 1 good guess. We still get to keep 6 because, again, right, good guess at 2. So 6 is the correct token going forward, or at least 6 is the correct token according to the big model. And so we have an output of 126. So again, 2 forward passes, 3 tokens. So still pretty good. And in the worst case scenario, you still get your 2 tokens with the additional overhead. So maybe you're slowing down. And again, that's why you want this Medusa stuff to be good. So let's talk about how you actually accept these things, or reject them rather. Yep, I think I heard someone. There's a question. All right. Well, so one of the techniques, and that's the technique used in the draft and target model paper, so the one that the authors try to improve upon, is this idea of rejection sampling. Now, there's an algorithm that is outlined here, and I'm not going to make you read all this, but I just put it here just to show you that there's an algorithm. I didn't make this up. At a very simple level, it's essentially doing the following. You have your token that you speculate, right? 2, 3, and 4, for example, as speculation tokens. They have an associated probability distribution. And I'm only showing like the probability for the top token here. So in this greedy decoding sense, right? Let's consider a greedy decoding setting. And what we do is, if the probability of the model itself, right? So upon verification, the model predicts the same token with a higher probability. We say, cool, right? The model agrees, we're going to accept it. What if the model has a lower probability than the speculation? Well, we don't necessarily reject it straight up. We actually reject it with a certain probability, which is given as the ratio of the like your target model and your speculation model. So the bigger the gap, the less likely you're actually going to accept the token. And in this case, let's say you accept 3, but then you reject 4 because, well, the probability of the big model thinks that it's very unlikely this token would be there. And so that's really the idea of rejection sampling. So let me post this here because this is like a little diagram of, but basically, yeah. So if the probability of the model is larger, you accept. Otherwise, you sample or you accept with some probability. And otherwise, if you reject, you still need to sample a token. And what you do is you actually subtract the probability distribution of the model and the speculation output, speculation model. And you only keep, you sample from the remaining positive terms. So the DeepMind paper, and there's another Google paper separate that's, I think, talking about the same idea. At least it looks like it's the same idea. They go into more depth about why this makes sense, but just, it's outside of the scope of this, I think, but that's the idea. So just you're aware of what's going on.
And that's for speculative decoding, not for Medusa, because you still need the 2 models here, right?
So this rejection sampling is just so you're still using Medusa. Rejection sampling is just a way to decide if you're keeping or rejecting a certain speculation. So this is one way of using. You could use this with Medusa.
So in the context of Medusa, I guess I was picturing this in my head as like the small model and the big model that you had in that Hugging Face diagram above.
Mm-hmm.
What is P speculation and P model in the context of Medusa? Are they separate models, or are they different heads of the same model?
So yeah, so in the context of the Medusa, at least the way I understand it, is that you still have these language model heads that are outputting probability distributions, right? So you don't have a separate model, but you have these built-in sort of language or additional Medusa heads, which are each outputting a probability distribution. So then you still have these speculation probabilities or probability distributions, which you can compare against the real model. So you still do 2 forward passes, but you just sort of, it's the same model in both cases. You don't have a separate model you're managing.
Gotcha.
If that makes sense. Yeah, but you still have, each Medusa head is still outputting a probability distribution, just like your draft model would. For every token, it would still output a probability distribution. In this case, the Medusa heads are in or part of the model itself, whereas in the other approach, that's a separate model altogether. Yeah, so that's the idea. So rejection sampling is one way of doing it, but there's another way that they talk about, and we might not be able to get to that, but just know that there are other ways of doing it that are arguably better because this has certain limitations, but the idea remains the same, is you're trying to come up with a way to actually keep or reject sequences. So here is the kind of the other big part of the Medusa paper. So because before we talked about, these heads aren't necessarily something new to Medusa, right? But I think this part actually is it's new, but also it's critical to the speedups that they report. And so I think that's what, it seems like it's worth talking about at least. And the idea comes in here is that, so what if you don't consider just the top candidate, right? So here we're considering the top candidate, right? So we're only considering one token essentially, right? And as a result, we get a single sequence. Well, what if we could consider, top KI or something like that? So like at every different head, we pick the top KI top tokens, right? So for example, and I here would be the index of the head. So let's say I have start word is Paris. I feed that to the model predicts is, and then head one predicts, we take, it has some probability distribution, but we keep the top two, and the top two are, let's say, the and a. And then head two in parallel, which now has a K of 3, predicts that the third token would be capital, city, bakery, something like this, right? So this actually gives you a bunch of options altogether. And these would be the options, right? So for example, it would be is the capital, is the city, is the bakery, is a city, is a capital, is a bakery. And you would like to consider all of them because that actually increases the chances of you accepting one of them. So you increases the chance, or at least what they observe is that this increases the chance of accepting a speculation, or like a candidate, I should say. And that's great because if you have a high acceptance rate, you have a higher speed up, as we discussed, because you get like a longer runs of correct guesses. But the only problem is that this could explode really quickly. So if you have 4 heads and you're keeping 4 tokens at each head, right, you can imagine this becoming a huge, like, you get this combinatorial explosion of options. And so what you can do is, yes, in theory, you could have all these options and then sort of batch them and then verify them all by passing this batch to the model. But that's not necessarily very efficient. And this can actually, maybe kills all your speed ups potentially because you have so many different candidates. So this is where this idea of tree attention comes in. If you're confused about this at this point, honestly, it took me so long to actually get to where I am with this even now. So I think the takeaway here is that as opposed to looking at one candidate, you can look at many candidates. And then with this clever attention mechanism, you can verify them all at once in a more efficient, faster way. And that's part of how you get the speed up, right? So that's kind of a key takeaway, if nothing else makes sense. But so this is the tree attention, right? So let's consider this example. You have your root, which would be, in my case, let's say Paris, or maybe is, I guess is. And then head one outputs 2 options. Let's say it and I, so k equals 2. So these are the top 2 tokens. These are not separately sampled, right? This is just, you have a probability distribution, you take the top 2, and they happen to be it and I. And then you do the same thing for head 2, where you keep 3 tokens now. And this gives you 6 options in total, or 6 paths. So what this attention matrix is saying is that I'm not going to attend to all the tokens that came before. I'm only going to attend to the tokens that came before in the same path, right? So let me see. Let me just so in this case, it is a node of this tree, right? And it attends to itself. I is a node of this tree. It attends to itself. Is right here cannot attend to I because I doesn't really come before it, right? It comes before it. So in this specific sequence, so in this case, is attending to it, right? In this case, this apostrophe is attending to it, but so the idea is this attention masks tokens in such a way that only the things that came before are in the same path. So only the ancestors or predecessors, I guess, can actually be considered this historical context, as opposed to every token that came before. Again, because in this case, it doesn't make sense. Like every token that came before isn't necessarily relevant, right? We want to consider specific paths. And so this tree mask, or tree attention mask, is the key. So I'm going to show some diagrams in a second, but basically, I think, at least what I understand from the code is that it's combined with the regular padding future masks, and so, but it sort of overrides it rather than necessarily combined. But it's not. But essentially, they're taking the mask that is normally generated by Hugging Face under the hood, and then they apply this tree mask over it to sort of, I guess, either overwrite or supplement it in a correct way. The way I see it is that in this case, like in the first row, the attention mask says that the model is only going to use the token it to predict something. then it's only going to use the token I to predict something. Then it's only going to use the tokens it and is to predict something, right? Then it's only going to use like it and apostrophe to predict something, and so on. So that's kind of what the mask is doing. And this did not get pasted correctly. Go here. Okay. And let me just do an example that maybe hopefully clears things a little bit up. So let's say we have our root, we have it, right? And it predicts, oh, sorry, the model predicts it. So now what we can say is that, well, or sorry, in our verification step, the model predicts it for the first position. So what we have this tree that of options, we can discard the left side of it because the model did not verify I, right? If we only kept I, for example, and the model predicted it, we would just basically say, oh, we got wrong guesses. So, we didn't actually gain any speed up and potentially actually, are at a disadvantage now. But because we're considering all these options, model predicts it, we're ready. We have this whole subtree here. Cool, right? So then we discard the left potentially and keep the right subtree. The next token that the model verifies is, and we say, all right, cool, we have that subtree. And so again, if we didn't have these options, we would discard this and say, oh, we got a wrong guess, right? If we just guessed D, for example, and we sort of lose on potential speedups. Now, this is all very tricky because it seems like, wait, this kind of, at least for me, one of the confusing parts is like, wait, this like, we're just generating all these tokens, but then we're generating them again and confirming like what's going on. So the way I understand it is, right, remember what we're trying to do is we do the speculative decoding or this Medusa decoding to guess tokens into the future quickly in parallel, right? So let's say 5 at the same time. And then we verify it with the model. But instead of trying to verify a single candidate, we want to verify like this whole tree of candidates. So that's where the attention mask comes in. This tree attention mask actually lets us do this like verification simultaneously. And so we're not doing a verification of a single candidate, we're verifying every possible path in this tree at the same time. And so that's how I understand it, at least. And I think that, and so that's why this idea is critical, is because if you were not able to do this in parallel, you're potentially wasting a lot of time, or you're not considering, you're discarding too many options straight off the bat if you're only considering one candidate, so you're limiting your potential speed up. But yeah, so, that's, there's a Reddit comment that I will share that I thought was helpful after reading everything. It's kind of, a good example that helped me a little bit. So, if anyone wants to see it or read it later on.
And then I have a question about how this relates to like, the traditional attention mechanism has like an n-squared property of the length of the sequence. This really seems like it depends on the number of predictions you take from each head. Do they have any like, what is the computational complexity based on how many heads you have, etc.?
That's a good question. I don't remember. Maybe they talked about it, but I don't remember seeing anything. I remember from the code that you're right. It does depend, right, on the K essentially, and the number of sequences you're considering, or sorry, the number, like the top K that at each head and so on. But in the code, this is kind of why I'm not sure exactly what they're doing, is that they take this combined attention mask that Hugging Face would return otherwise, and then they sort of slice out a chunk of it. Or like, if you think of the attention mask as being this 4-dimensional tensor, by number of batch, number of heads, sequence length by sequence length, they only apply their tree mask to up to the point that, whatever number of sequences that they generate here. So I think you still maintain your quadratic complexity because you're not replacing the original mask, as far as I can tell. You're sort of just augmenting it in this way. Don't know exactly what that augmented mask looks like, but I from what I can tell from the code, you still maintain that quadratic complexity in terms of the attention.
Gotcha. Because I was picturing that blowing up if you had more heads, even like just from a memory perspective, not from a compute perspective, because you have a bunch of zeros. But
yeah, I'm not 100% sure, unfortunately, because I was trying to get as much of it as I could from the code, but it was a little bit tough to read. There's a lot of stuff going on, and
yeah, for sure.
So, but if that offers any insight, they're taking this original combined mask and they're doing something to it. So, not sure what the limits are, because your attention mask is sort of limited by the sequence. Like, you have the sequence length by sequence length. So I don't know how they handle different cases, but from what I can tell, they're taking the original combined mask, they're doing something to it. So it seems like you would still maintain at least that quadratic complexity.
Cool. Thanks.
Okay, so I'm gonna quickly go through the remaining parts because I think that this explains the main idea of what's going on and what they're trying to do. But a big question is, so first of all is, well, how does this work? And two, how do you actually add this to an LLM, right? So let's quickly look at how you would add this to an existing LLM. And the first approach, Medusa 1, is actually exactly what you'd expect, I think, is that you take a bunch of these heads, you freeze your base model, their base LLM, and you just train your attention heads on whatever data set you have. You might not have a data set to train on, and they propose a technique called self-distillation to do this. I won't go into it, but the idea is you're basically pulling data from the model itself with like a trick, essentially. You take a different data set that's similar, and then you try to get the model to generate responses. So you have your data set you can then fine tune on. But the idea of Medusa 1 is you have your attention heads, you have your Medusa heads that you fine tune separately as the remainder of the model is frozen. These are pretty small, so you can actually do this relatively efficiently and quickly on a single GPU. Of course, depends on maybe how many heads you have and the data set and so on, but still, you're not fine tuning the whole LLM. The trade-off is that you're actually suffering performance. And remember, performance in terms of how good the predictions are is also related to the speedups. So you can get better speedups if you actually train the two together. And there are different strategies, but you can combine the losses. So you have some factor that's applies the Medusa 1 loss, which we have here. You have a smaller learning rate for the LLM because the LLM is essentially trained. You don't want to shift the distribution of the LLM too much, or ideally not at all. And then the learning rate for the Medusa heads is much higher. And then finally the warm up. So you actually do Medusa 1 first and then train the two together. As far as I can tell, the wording is a little bit confusing in the paper, but the idea is that you're doing some kind of, you're training these Medusa heads separately until they get a little bit better, and then you train the two together. And I think you can combine the different strategies if you wanted to. So that seems to be one of the things that they refer to.
Cool. And then we have another question in the chat. I think the first strategy is really cool to our point before of like you could potentially add these heads on top of any other backbone architecture. So if we were doing like our Mambusa thing, I feel like that strategy would work. But the other question we had in the chat was, can you get some extra details on what verifying means? I would have thought it meant having a big LLM generate each token, but that would need to be done sequentially. And at that point, there's no advantage over using the big LLM directly. So can you talk a bit more about the verification process?
Yeah, that's a great question. And, I think it took me several passes through the paper to actually make, and not even this paper, but the other papers that they reference or that they go back to really kind of get a sense of what's going on. But I think this is a good visual. So you generate your candidates, right? So your speculation sequence, right? You speculate what the sequence could be. And then you feed it to the big LLM and you'd say, okay, well, you're still using the big LLM, right? It still takes time. The main difference is that if you were to generate this sequence with the big LLM, you would need 5 forward passes. You can verify this in a single forward pass. Now, what does verify mean? Essentially, in my example here, you have your 0 token, which you're given, right? That's like your prefix. You guess 1 and 2. You pass this through the big LLM all at once, right? And again, remember, that's the whole, like the transformer, the big deal about it. One of the big deals, at least, is that you have these kind of parallel, you can treat every token in parallel. You generate 3 separate distributions. And then because the transformer is trained to predict the next token, it would be predicting, like you're asking, what would the big transformer predict from token 0 or as the next token for token 0? And if they agree, so your guess and the big LLM agree, you say, cool, I got it right? So I keep this one. You do the same thing for the second and third. Now, I am talking about it sequentially, but this forward pass gives you these 3 distributions at the same time. So you're not actually doing this one by one. So that's where the speed up, and that's kind of, the verification here is good because, the verification is necessary because you want the feedback of the big LLM, what would it output? But you don't want to have to do 3 forward passes for it. So you feed this the speculation sequence, whatever you speculate the sequence to be through the LLM, get 3 probability distributions simultaneously, and then compare what the big model thinks to what your guesses are. And your guess would, might be a probability distribution, not necessarily a single guess like this. Does that make sense as to what it's doing?
So to sum that up, Zach says, would that be n small LLM passes and 1 big LLM pass for verifying?
In the case of, yes, in the case of speculative decoding, it would be n small LLM passes and 1 big LLM pass. In the case of Medusa, you would be doing in parallel, let's say n, you would speculate n tokens. So you would do 1 forward pass through the big model to predict this token and these, guesses by the heads, and you could have like however many heads you want, up to k heads. So that's 1 pass of the big model, and then the second pass of the big model is the verification. So again, same idea. You have your candidate sequence that has a bunch of guesses in it. You pass it through the big LLM so that you can see what the probability distributions would look like, but in a single forward pass. If
Got it. So then when you scroll down, that's where you're getting 2 forward, or scroll back up a little bit. You said 2 forward passes equals 4 tokens or something.
Yes,
Yeah.
exactly. So the first forward pass is to generate this, this first token, the actual model token, plus what the Medusa heads output, and then the second pass is to do the verification.
Got it. That's clever. Okay, thank you. And then
yeah, go ahead.
Kaiser also asked, do you have to decrease the batch size to proportionally take the number of speculative paths to take?
That is a great question, and I was actually going to mention this at the end. They
Nice.
only talk about, so like one big thing that they mentioned in the paper is that this only works for batch sizes of 1. And they're working on figuring out how to make this work for larger batch sizes. Their argument is that in a case of a personal use, right, if you're using for LLM for personal use, right, you're not like OpenAI serving a bunch of things at the same time, 1 is fine, but of course, a limitation, a substantial limitation. And I guess they're working, at least all their, like the comments that I've seen on Reddit by the authors or collaborators is that they're working on figuring out a way to make this work for batch sizes that are larger than 1. But great
So
question.
that
I think
means at training time too, they're only doing 1 batch?
that's a good question. I am not sure about that, but I think so, because they need this. Maybe not, because at training time they have this cross entropy loss, but it's just trying to predict. Where is it? Somewhere here. They're just trying to predict. They're just trying to get the head to predict tokens into the future. I'm not sure if they're using this tree attention at that stage. So you might be fine using, though I might be wrong on this, but I feel like maybe you're okay training on batches, because I think what limits the batch is this tree attention, potentially. Not sure, not 100% sure, but I didn't see anything mentioned about that you need to have a batch size of 1 for training. So,
Got it.
which leads me to believe that maybe you don't.
Cool. Good stuff to dig into after.
Yeah, and one last part, so the results is, I'm just going to quickly go over this, but the idea is basically they show that Medusa 1 gives you a speed up to 2.83x on models, 7 billion model, 13 billion parameter model, to kind of show you these different speed ups. It's also task specific. Now, the first thing that I couldn't figure out was, why does it depend on the task, and why does it depend on which Medusa approach you use? And this all ties into, if you have better guessing, you can go for higher runs, or you can get longer runs of correct guesses, and that means you can generate more tokens in less forward passes. So the quality of the model directly relates to the speed, or the speed up. In some sense, if you think about it, right, in like a very not edge, but like a corner or extreme case of this, you just say, forget the big model, I want to go faster, I'm just going to use a small model altogether, right? And then you're trading essentially speed for performance. But so, I think it makes sense that you get this trade-off. But yeah, that's the idea. So the speed ups are different because it depends on how well the model performs, how good the guessing is, essentially. And yeah, they show you some more benchmarks or results for larger models too. And they have these different metrics like acceleration rate, which is just a question of So the number of average tokens you get per decoding step. So in a regular, transformer, normally you would get 1 because every forward pass gives you 1 token. In their cases, you have those, you get higher because you can on average get more tokens per forward pass, as we discussed before. The overhead is like the additional overhead, as I understand it, of doing this fancy guessing, decoding, and all that stuff. And the overall speed up is just the kind of the ratio of the two. And quality here is, I think, the average scores on the benchmark that they're using. And the whole point of this is that, right, you can get speed ups while maintaining the quality. And I agree. I think Medusa 1 is really interesting because I can imagine doing it like, they're using it 1 GPU, so that's really cool.
In the results section, can you scroll back up to the different tasks?
Mm-hmm.
It had like math, coding, extraction. This feels like it would be helpful, especially in these like math and coding problems. I remember in the Tree of Thought paper, they were talking about how predicting multiple possible futures are really helpful for things like math, where if you mess up one number in the sequence, you're kind of out of luck for the rest of the sequence. So do you have intuition on that might be why these numbers go up as well? Or is that speed up? That's not accuracy. I was reading.
Sorry, yeah, this is speed up. They're connected, and so they do mention that you get there seems to be a boost, right, in terms of coding and math, as you said, and so they mention that their Medusa model is doing particularly. They say it's doing particularly well on those tasks. So I'm not sure if like this multiple decoding heads predicting into the future and having this tree of different options is, it's possible that, yeah, as you said, I think that's an interesting connection with the Tree of Thought paper, that if you have a bunch of these options, you're sort of potentially doing better because you have a higher chance of that you found the right choice. Yeah.
Makes sense.
And
Cool. Well, I know we're running close on time here. I'm gonna kill the recording just in case there's any offline questions. But round of applause for Daniel, for people watching on YouTube, and I'll kill it here if people want to.
Thank you, Daniel.
Thanks, Daniel.